It's recording.
Have Ron Buta speak to us. He's one of my favorites among the members of the congregation who talk. And so, Ron?
Thank you. Let me get this started. I've got a few pictures to show. There we go.
I really wish I was using that tripod. I'd be quiet. Deal. Yeah.
Well, here I am again. The title of my presentation is called Such Things Exist. The Joy of Exploring the Universe. Let's get this up, these come up.
I might as well.
50 years ago, in the spring of 1965, I had a revelation. A chance viewing of the bright naked eye star Sirius through a window at my home in Baltimore led me into the world of science, specifically the world of astronomy, and my life was changed forever. Seeing the star led me to a small star book, and in that book there was a picture of the Andromeda Galaxy, the nearest major galaxy beyond our own. When I learned that Andromeda was 750,000 light years away, my imagination went into the stratosphere. And at 13 years of age, astronomy became a dominant force in my life. Now, it's hard to believe that such a small event could have such a large impact on a person's life. But here I stand as a witness to it, feeling much the same about it today as I did all those years ago. But now, I must ask, after 50 years of doing what I do, telescopic viewing and observing, advanced study and research, professor, what more is there for me to learn? Do I know everything? My topic today, Such Things Exist, is a catchphrase that captures my answer to that question. With it, I am referring to what I learned when I began to examine some of the large research databases that are available to astronomers today. In these databases are images of hundreds of thousands of galaxies, very few of which have been studied in detail by anyone. As an experienced galaxy morphologist and classifier, that's what I do, I'm a professional astronomer, I am naturally drawn to examine what the new databases reveal. What do they have to say? Now, while I could examine the images as they are and not get too philosophical about it, that is not stand up here and get philosophical, I knew that looking at the thousands of galaxies would be more than me just being a professional astronomer doing what professional astronomers usually do. I would also be exploring the universe at a level I hadn't experienced before. And each image I examined opened a new door because the quality of the images was so much higher than in my previous experiences. I was able to see things that I hadn't noticed before. But before going on, I wanted to provide a little bit of background. I wanted to say a little bit about why we should study galaxies. Why should they be the focus of a person's life? A galaxy is a massive system of stars, interstellar gas, dust, and other forms of peculiar matter, bound by gravity into a single unit. Most of the stars in the universe are concentrated in galaxies, with very few in the intergalactic space between galaxies. Now, the combined light of all the stars and can make a galaxy so luminous that even with a small telescope you can see them from hundreds of millions of light years away. With large observatory telescopes we can see galaxies billions of light years away. And with the Hubble Space Telescope we can see them so far away that we are receiving the light they emitted not long after they formed. We're looking way back in time at these things, as far back in time as possible. They're not things to be taken lightly. Galaxies are important because they're the only places where the walk of stellar life, the walk of life of the stars, can proceed through all of its phases, allowing later generations of stars to have a close connection to the earlier ones. Galaxies provide the raw materials for star formation. And these raw materials, in the form of interstellar gas and dust, are made from countless generations of earlier stars that either silently or violently, that is by explosion, recycled some of their gases enriched in heavy chemical elements back to the interstellar medium. Dust is the smog of stellar evolution. Stars pollute. They really do. But pollution is good. That pollution is good. Dust is good. Now, dust collects in the plane of a galaxy over a very long period of time. And then new stars would form out of this enriched material, which would then have a greater proportion of the kinds of materials needed for planet formation and living creatures. Now here I have a picture of a lovely spiral galaxy. I'm going to show you what I mean by the dust collecting in the plane. This is a very highly flattened type of object. If you could see an edge on, it would look different than that. So let me show you an edge-on view of the dust layer. There. Now this is what I mean about dust collecting into the plane of a galaxy. This is the side view of a spiral galaxy called an edge-on view. And there's the nucleus pointing out just above the dust lane. But the dust is very important. That's where the stars can form. The new stars can form in that layer. Now, seeing something like this through a telescope, especially a large telescope, and I'm a guy who dreams big. I think really big. I don't want little telescopes. I want something big. So I dream big. Seeing a galaxy with a big telescope stirs my imagination. I know that I'm looking at something just like the Milky Way, but hopelessly beyond the reach of mankind. It would take, for example, more than 1 billion years for a spacecraft like Voyager 2 to reach the Andromeda Galaxy, which is the nearest big galaxy. More than 1 billion years. That's how far away a galaxy can be. And among the billions of stars in a remote galaxy, one has to wonder, what else is there besides what we can see? The stars, gas, and dust, and now we have the issue of dark matter, which is even more mysterious. What would it be like to fly through intergalactic space, hopping from one galaxy to the next, to see what they are like, to view them from different vantage points, watch them change over time? What events have happened in other galaxies that we will either never know about or will not know about for millions of years, because it takes time for the news, millions of years for the news to reach us from these things. Now, as interesting as it might be to imagine visiting a galaxy and seeing its individual stars, and I always think about that, think about it a lot. The reality is that we can't see the individual stars in most galaxies, even with the extraordinary power of the Hubble Space Telescope. Instead, we see the unresolved glow of millions and millions of faint stars, which is what this is. When you see an individual star in a picture like this, those are foreground stars in our galaxy. They're not part of that galaxy. What you're seeing here and here, now here, is the unresolved light of millions and millions of faint stars that you can't see, you can't resolve. You get a bigger telescope if you wanted to. These unresolved masses of stars define what we call the structure of galaxies, what astronomers call galaxy morphology. Galaxy morphology is about what you see in the unresolved glow of the starlight of the galaxy. Now, seeing a distant galaxy through a telescope is kind of like seeing the Milky Way with the naked eye. There are millions of faint stars, too faint to be seen with the naked eye, that give the Milky Way its distinct milkiness. And even this is when we live in a time when a lot of people don't even get to see the Milky Way because of light pollution. But if you could see the Milky Way from your location, its distinct milkiness is due to the unresolved glow of millions and millions of faint stars. Now, unlike most other galaxies, however, even the slightest optical aid resolves the glowing star clouds in the Milky Way. And resolving Milky Way is so easy that it was one of the first things Galileo noticed when he looked at the sky with a small telescope in the early 1600s. Now, what makes galaxies so interesting is that the unresolved light of all those millions of faint stars does not concentrate in random glowing patterns. Patterns are not random, but into highly organized and I think sublimely beautiful structures. One such highly organized structure is the spiral shape. I'm going to show another one. That's a stunner. Beautiful spiral galaxy where you see the unresolved star clouds following these distinct curved structures called spiral arms. These were first discovered in the 1840s in Ireland.
I didn't know that.
Now, most large galaxies have this kind of structure. The arms are narrow, curved, glowing features that wind outward from the center. In this case, they're winding outward from a ring. There's the center. Spiral arms are interesting because they're often lined by newly born stars that light them up like a Christmas tree. And you can see the little patches, the little knots. Each one of those little spots is a cluster of massive young stars that have formed in these spiral arms. And, well, that's an interesting aspect of spiral arms. It's not clear why that should be the case, but that's the way it is. For more than 150 years, the spiral shape has added a mystique to galaxies that continues to this day. That's one of the reasons I'm here, is because of that mystique, because I am fascinated by that spiral structure. It is still not known precisely how spiral patterns develop. There are indications that this kind of thing could be generated by an interaction with another galaxy. And this one has a big companion, not visible in this picture. Maybe that generated the spiral. But sometimes they don't have companions, and they still look like this. So maybe there's another way. These galaxy spirals are highly flattened, and such systems actually are unstable. It needs to be possibly unstable to forming these patterns naturally. Now, there are other patterns besides spiral arms that are seen as well that I find interesting that you might not be familiar with. One is an unusual feature called a bar. So I'll show you a barred spiral. Because bars are so much fun. Oh, here's another spiral. That one's a beauty. And again, the bright stars are foreground stars in our galaxy. There's a barred spiral. This linear feature here is called a bar. They're usually made of old stars, but in this picture you can't tell. But I'm going to show you a picture where you will be able to see that. They're made of old stars. It crosses the center. They can be 10,000 light years long, and they're still straight for 10,000 light years or more. And bars are actually better understood than spiral arms. In a way, a bar is like a childhood disease that lingers into adulthood. And here's why. If a galaxy has a significant amount of energy tied up in organized motion, and what that means is orbital motion around the center. There's a lot of energy tied up in orbital motion. They're unstable to the formation of a bar. The only way for a galaxy to cure itself, and they can do it sometimes, of a bar, is for random motions to become important. Less organized rotational motion, more random motion can cure the bar. But a lot of them aren't cured because most galaxies have a bar, including our galaxy. We have a bar. But they can cure themselves. Now, a ring. Let me see if that's the next slide. I'll show you about a ring. Yes, I'll show you that this is a ringed barred galaxy where you have a bar. And you see these narrow things here? Those are dust lanes. They're interstellar dust in a highly organized pattern. And this is called a ring. Now, a ring is a circular or elliptical enhancement in the light distribution of a galaxy. It may be a closed feature, or it may be made of tightly wrapped spiral arms. Now, rings are very special to me because they were the subject of my, I hate to say it, 981-page PhD thesis dissertation. 981-page this size dissertation in 1984. My dissertation was called "The Structure and Dynamics of Ringed Galaxies." I wanted to understand these rings. I had first learned about the rings in 1975 when I was a physics graduate student at Michigan State University. This is before I went to the University of Texas. My faculty advisor, Dr. Susan Simkin, introduced me to them through a small research project on one particular galaxy that had an extraordinary ring of star formation. It was a ring around the center lined by knots, each one of which were clusters of massive young stars. I could not believe such a thing existed. I didn't even know it existed, but I was a graduate student and I was learning. I was so intrigued by galactic rings that even after I finished my 981-page dissertation, I spent another 10 years cataloging a large number of examples. And this required that I examine the structure of thousands of galaxies on these charts that were taken in the 1980s. Now, what appealed to me about these features, and also explained how they could be, and it also explains how these rings could be lined by star formation, is the likely close association of these features with what we call orbit resonance. An orbit resonance is a place, like in a galaxy, or in the rings of Saturn, where material moves in step with something else. In the case of a galaxy, the rings are closely associated with strong bars and spirals. You see, a strong bar. A ring is a feature that is thought to form in response to the presence of a bar, which rotates in a coherent pattern. The dynamics of a ring in a galaxy is similar to that of the rings of Saturn, but with an important difference. In the rings of Saturn, ring particles, and the rings of Saturn are made of small objects. Ring particles that orbit in step with Saturn's moons are said to be in resonance with those moons. And resonances are places where repeating configurations cause collisions. In the rings of Saturn, these collisions clear a gap near the resonance, and you have the Cassini division in the rings of Saturn. But in a galaxy, it's tenuous gas clouds that would collide, and they would collapse to form stars, making the resonance region into a bright ring rather than a gap. And so, in the rings of Saturn, we would see a gap here, but in a galaxy, we see a bright ring, because when gas clouds collide, they collapse to form stars. But when particles collide, they clear the gap. So you can relate this type of thing to something nearby. It's interesting. Now, the symmetry of rings, bars, and spiral arms becomes even more remarkable when we consider how large this thing is. This thing is huge. This ring is itself is at least 10,000 light years across. The Milky Way, for example, is about 100,000 light years in diameter, and it is a spiral. It may not look like that. But in order for something so large to have such organized structure on a scale like that, the force that must be at work to do it has to be able to act on a very large scale. The only viable candidate is gravity. Gravity is molding these features. Gravity molds the structure of galaxies. And it is on the scale of a galaxy that we get to see gravity at its artistic finest. Ain't it the truth? Now, galaxies are also interesting for what they reveal about the universe in which we live. Nearly 100 years ago, the science of spectroscopy had become a major part of astronomy. Through an eyepiece of a telescope or on a photographic image, we simply see how bright a galaxy is and what its structure is like. The bright ones often look very similar to those much fainter, and we might deduce that the fainter ones are simply more distant than the brighter ones. But spectroscopy showed one other thing. Something else was going on. On average, galaxies are receding from us at speeds proportional to their distances. Farther they are away, faster they are moving away from us. And this observation, credited to Edwin Hubble, made what we call the universe a physical object. it implied the universe is expanding. And not only this, that it had a beginning. That's very bizarre. The world of galaxies brought humanity the subject of cosmology, the study of the origin and evolution of the universe. Now, it wasn't that long ago that people started noticing galaxies. Galileo's telescope in 1610 could only reveal one other galaxy well. And it was nearly 200 years later that telescopes improved enough to reveal more. And in the 18th century, large numbers of nebulous objects were discovered across the sky and cataloged. And at the time, it wasn't actually known what these objects were. Many looked like small clouds of glowing gases scattered among the stars of the Milky Way. And almost 100 years ago, Edwin Hubble proved the great nebula in Andromeda was a galaxy like the Milky Way, but lying far beyond the Milky Way's border. Now, almost all of the other nebulous objects the early observers cataloged were found to be galaxies much more distant than Andromeda. The size of the universe increased dramatically with Hubble's discovery. Now, in the 21st century, it's fair to say that we know a lot about galaxies. We have a good idea of how galaxies form. We know how massive they are. We know how large they are. We know what they're made of. We don't know everything about them, but we know a lot. But much of that, we even know how they might change over time. But much of that knowledge has been acquired very recently. Accumulating data has been slow. I mean, at one time it was slow, often one or a few galaxies at a time. Up until 1985, imaging was done exclusively with glass photographic plates. And although the staple of astronomy for more than 100 years, photographic plates were very inefficient and had to be exposed for a long time to get a good image. Then in 1985, an 800-pound gorilla came onto the scene. Can anybody say what that was? An 800-pound gorilla came onto the scene. A charge-coupled device. And this changed not only astronomy but the world. And my 981-page PhD thesis was written at the end of the photographic era, so I have no CCD data in my thesis. Anyway, CCDs are the basis of most modern digital cameras, and a CCD could make an image of a galaxy in a few minutes that would have taken more than an hour with photographic plates. It just revolutionized the whole science. In the 1950s, astronomers at Mount Wilson and Palomar observatories carried out a photographic survey of the northern sky that provided images of thousands of faint galaxies. The images were recorded on large plates, each covering a significant swath of sky. I recall being amazed, and I was a lot younger when this happened, and what these pictures showed. Just about every galaxy I knew about had a picture, and I knew about a lot of them at the time, because I always know about them. I always have wanted to. And although I did have a, quote, such things exist moment with those images while making my catalog of rings, it was the Sloan Digital Sky Survey that inspired me to make this presentation. The Sloan Digital Sky Survey, or SDSS for short, is one of the most remarkable scientific enterprises ever carried out. It used digital images to take images of the large portions of the sky. The use of digital imaging to cover a large area of sky with sensitive CCD detectors provided imaging data of more than 1 million galaxies. And not only this, with such data it became possible to create color images. This is not in color, but what if we could see them in color? Color images of all of these galaxies, and it was the first time such a thing was possible. And seeing a galaxy in black and white, you can look at the picture and say, I can see a lot about this galaxy in black and white, but when you see it in color, I'm going to show a couple color images. You can tell what kinds of stars make up the features seen in galaxy morphology. Like if I see this in color, would I see that the same stars that make up this feature are making up that feature? So you can tell. Now the SDSS was started in 2000, but it was in 2013 when I personally had a chance to examine the galaxies myself. And since then I've classified more than 9,000 at a rate of 1,000 a month. And there was a big paper written on 300,000 galaxies from the Sloan Digital Sky Survey that a large number of amateurs have classified, and I estimated it would take me 20 years to do 300,000 galaxies. What did I see in these images that elicited this view? So now I'm going to show you a few more pictures. What else do I have here? Okay. Now, remember this picture I showed of an edge-on galaxy? That one there. This feature here is called the bulge. And in our galaxy, the bulge is in the direction of the constellation Sagittarius. And if you go to Chile in July on a moonless night, go to a mountaintop in Chile, the central bulge of the Milky Way stands overhead. It's incredibly bright. But just look at what it looks like. It's kind of roundish. And then you look at these other edge-on galaxies, and they have X patterns. And look at the thin dust thing. I had never seen anything like that before. And here's another one of these bright features, which are probably related to a bar, seen edge-on. So this is one of them. So these are two of my such things exist moments that I had looking at this database. Let me show you what else. Look at this one here. What do you see in this picture? You see a bar, and you see spiral arms, but look at the color difference. Now, when you see, this is slow digital spassive image, when you see yellow in a picture like this, you're seeing the light of old stars, older than the sun, very, very old stars. But when you see blue, as in the spiral arms, you're seeing young stars. So you see that bars are made of old stars. And if they're made of old stars, they're made of a lot of mass. Whereas spiral arms are fleeting features made of young stars. And young stars evolve faster than, and these young stars are massive, and they evolve faster than low mass stars. And so if you were to take a picture of this galaxy and say 10 million years after this one, it would look a little different because the 10 or 20 million years, because these things in these spiral arms evolve fast. They come and go. Now let me show you, and also here's another thing that's inspired me. Look at these spots. They're like handles on the bar. How in the world did those form? And it must be a dynamical phenomenon. And what's this? I think that's a background galaxy, but it looks like my spots. And so I'm wondering if these two spots are related to that. And let's see what else I